we were doing organic chemistry. I told you about benzene. This right here is the old structure of benzene, where each alternating bond was a double bond, right? It is C6H6. And this structure was refuted for various reasons. We'll see that. And this is now the acceptable structure of benzene, where you have 6 carbons arranged in a hexagonal ring with a pi ring in the middle right here, made up of 6 electrons, one from each carbon, right? Then benzene in C6H6, each carbon is sp2 hybridized, right? Therefore, benzene has bond angles of 120 and it's trigonal planar. But it's a planar molecule. Why? Because obviously it is sp2 hybridized. Then benzene, the initial structure of benzene, which was this with alternating double bonds, is refuted. Why? Because each alternating bond was a double bond, and this structure, if you see, means that this looks like an alkene. But benzene does not decolorize bromine, so that means the structure is not correct, obviously, because if it was an alkene or had double bonds, then it should have decolorized bromine. Then it does not react with or oxidizes with KMnO4 either. Alkene does. This doesn't. So this is also refuted for that reason. And also because all the bond lengths, despite being single or double, all the bond lengths are the same. The bond strengths are the same. So that means this can't be true, because in a double bond, the bond strength is more compared to a single bond. So this structure was refuted. Then we saw properties of benzene, and even despite having a delocalized firing, because the molecule is non-polar, it will be a poor conductor. Benzene right here has, you can make benzene undergo substitution reactions, where you can remove one hydrogen and replace it with something else, a side chain. We can have one side chain, which is called monosubstitution, or you can have more than one, two, three, four, five, whatever. That is called polysubstitution. Let's see monosubstitution, which are the parent compounds. If you have a methyl group attached, we will call it methyl benzene. If you have a chloro attached, call it chlorobenzene. Nitro group attached, nitrobenzene. OH attached, called a phenol. If you have an amine, this is called phenylamine or benzamine. If you have an aldehyde, this is called benzaldehyde. If you have acid, we call it benzoic acid. If you have a nitrile, we call it benzynitrile. Then you have polysubstituted benzene derivatives as well. Right here you have, if you have substitutions on carbon 1 and 2, we call those the ortho positions. If they are on carbon 1 and 3, we call them meta positions. And if they are on carbon 1 and 4, we call them para positions. Right here you have them on 1 and 2. So we call this 1,2-dichlorobenzene, 1,3-dichlorobenzene, 1,4-dichlorobenzene, 1,4-dinitrobenzene, 1,3-dinitrobenzene. Now between OH and Br, you've got to know the list of priority for benzene derivatives. OH and halogen. OH is more important. So this will be carbon number 1, and therefore Br is on carbon number 2. So this will be 2-bromo, and this would be what? Phenol, right? This will be carbon 1, 3, and 5. This will be 3, 5 dibromophenol. Then this would be amine and chloro. Amine is more important than chloro. So this will be 3-chloro phenylamine. You can also call it benzamine. This will be 4-nitro benzamine or phenylamine. Now between acid and alcohol, acid is more important. So this will be 3-hydroxy benzoic acid. This would be 3-chloro benzoic acid. This would be ethyl and an amine. Amine is more important. So this will be 3-ethyl phenylamine, right? So that's how you name polysubstituted benzene derivatives. We saw the reaction of benzene combustion, complete and incomplete. Even though benzene is liquid and a reaction is highly exothermic, it releases large amounts of energy. You can't use it as fuel because benzene is carcinogenic. It has a high octane rating of 101, but because it's cancer causing, you can only use it as an additive up to 1 to 2%. You can use its derivatives as additives as well. Then you have incomplete combustion right here, which causes a smoky flame of soot or just carbon. Now we will move on. So we've seen this reaction, combustion. Now we will move on to the other two reactions, free radical addition and electrophilic substitution. Let's see free radical addition first. Now, free radical addition is where you add something on the benzene ring. Yes. Now, the first example is chlorination. What will be your reagent for free radical addition? Now, to make free radical, if you remember from alkanes in AS, we used to make radicals or used to get radicals in the presence of UV light. Yes. So you are doing chlorination here. So you're adding chlorine. So your reagent would be what? Chlorine. It would be chlorine in the presence of what? in the presence of UV light. So your reagent would be chlorine gas and your condition would be UV light. Now what will be the reaction? Let's see. So you will have benzene ring right here, and this benzene ring along with chlorine. So this will undergo addition reaction. And what happens in addition reaction? You get rid of the pi ring. So you get rid of this pi ring. And what do you have instead? This pi ring is gone, and on each carbon of benzene, the pi ring is gone, and on each carbon you will add a Cl. So you had C6H6. Yes, this is what benzene was, C6H6. And now you will remove this pi ring. This pi ring will be lost, and you will have a Cl here, a Cl here, a Cl here, a Cl here, Cl here, and a Cl here. You already have the H's also. I'm not showing the H's. You will have H's2 on each carbon. The pi ring is, however, lost. And this happens in the presence of UV light, and you will obviously heat this. And when you balance it, this will become 3Cl2. This becomes C6H6Cl6. And when you name this, this will be 1, 2, 3, 4, 5, 6 hexachloro. So this is hexachloro cyclohexane. Now this is no longer benzene. Do you see? Because benzene is when you have a pi ring in the middle. This is benzene. If you don't have a pi ring, then this becomes what? Cyclohexane. So this right here is 1, 2, 3, 4, 5, 6 hexachlorocyclohexane, right? Let's now move on to the next type of free radical addition reaction where you have hydrogen being added. So your reagent will be what? Hydrogen gas. Now, if you remember free radical, if you remember electrophilic addition of alkenes, in alkenes, we used to add hydrogen as well, if you remember, and we used to add hydrogen in the presence of nickel catalyst. Do you remember that? So this right here, the condition for this reaction will also be what? Nickel catalyst, and the temperature would be at 150 degrees Celsius. So you will have nickel catalyst at 150, and that will give you a hydrogenation of benzene. So right here we have benzene. On each carbon you have a H already, but you are adding more H to it. So what will happen in free radical addition? In free radical addition, the pi ring will disappear, and on each carbon you will have an H added. You already have one H, and one more is added to each carbon. So basically we will have 2 hydrogens on each carbon. Clear? So this right here is your cyclohexane. What do we make? Cyclohexane. That's your product. That is C6, and on each carbon you have 2, so that's C6H12, right? Now, if you remember that this reaction is happening in the presence of nickel catalyst at 150 degrees Celsius. Yes, so this is your catalyst and temperature conditions, and you will require 3 moles of hydrogen. Now, if you remember when we did electrophilic addition of alkenes, where you added the hydrogen to an alkene, if you remember, that reaction was also called reduction. Why? Because if you remember, hydrogen was a reducing agent, along with lithium aluminum hydride, sodium borohydride. So, so we have cyclohexane right here, and this reaction is also called a reduction reaction. Why do we call this a reduction reaction? Because if you remember, we saw reducing agents. We had hydrogen, lithium aluminum hydride, sodium borohydride. These were all reducing agents. Hydrogen is also a reducing agent, right? So since hydrogen is a reducing agent, we can call this reaction what? Reduction reaction as well. Is this clear? All you got to do is you got to take your reagent, remember the reagent and their conditions, and remove the pi ring in the product and add the reagent to each carbon. If you're taking chlorine, 1 Cl will go on each carbon. If you're taking hydrogen, 1 hydrogen will go on each carbon. And your product will become an alkane, a cycloalkane, right? And this is no longer a benzene. This is no longer a benzene. The pi ring is gone. Is this clear? These reactions, they are what? Free radical addition reactions. Is this understood? Moving on to the next type of reaction. So we already saw combustion. We just saw free radical addition. Let's now move on to electrophilic substitution. Now, electrophilic substitution in benzene is of 5 types. There is one where you substitute a hydrogen with a halogen. So that is called halogenation. Then we have a nitro group involved, so we call that nitration. Then there is sulfonation. Then there is Friedel-Crafts alkylation. So you have Friedel-Crafts alkylation and you have Friedel-Crafts acylation. So you have Friedel-Crafts alkylation, Friedel-Crafts acylation, sulfonation, nitration, and halogenation. We will see each of these individually. First, let's generally see how the mechanism of electrophilic substitution works. Electrophilic substitution of benzene occurs in two steps. And what are the two steps? The first step is the rate determining step. If you remember, what is a rate determining step? The rate determining step is the slow step. So the first step is the rate determining step or the slow step. And step number two is then obviously the fast step. So this happens in two steps. First step is slow and the second one is a fast step. Now, let's see how this works. So let's see the first step. In the first step, you will form a 4-valent carbocation intermediate. Now, what does that mean? I will just show you. So this is electrophilic substitution. If you remember, what is an electrophile? An electrophile is electron or negative loving. So it itself should be what? Positively charged. Yes. So let's see. Now I'm taking a general benzene reaction with an electrophile where I'm representing the electrophile as E plus, right? So this is your electrophile. What will happen? Now the electrophile has a positive charge. Benzene has the pi ring, which has the electrons. Now, if you remember the pi bond, what was the pi bond? It was an electron cloud above and below the nuclei. Yes. Likewise, the pi ring is also an electron cloud above and below the ring. So basically, you have this cyclohexane, the hexagonal ring, and above and below this ring, you will have what? Electron clouds. Yeah. Now, can I say that since the electron clouds have pi electrons, so that will be the negative side where the electrophile will attack. Because what is the site of electrophilic attack? It will be the negative electrons. And where are those negative electrons? In the pi ring. So the electrophile will attack the pi ring. The pi ring has the electrons, therefore you will show an arrow from the ring to the electrophile. Yes, because if you remember, I told you, you always show the arrows from the donor of electrons to the recipient. So you show you show an arrow from the electrons which are in the ring to the recipient, which is the electrophile. Yes, and this right here, I told you, is the slow step. Why is this the slow step? Because I told you the first step is the rate determining step. Now, what will happen here? Let's see. What you make is, you know that this pi ring is distributed evenly across the 6 carbons. Yes, this pi ring was distributed evenly across these 6 carbons. Now, what happens is that when you have the electrophile attack the pi ring, this pi ring breaks. And because it loses an electron, there will be a positive charge. And this electrophile will bond here and will attach to one of the carbons. Yes. So this attaches to one of the carbon and the carbon gets a positive charge. And we call this a 4-valent carbocation. Carbocation because it has a positive charge, 4-valent because if you see, we already had a hydrogen here because on each of these carbons, we have a hydrogen already. Yeah. And now you have an electrophile as well. If you look at this carbon is making how many bonds? It is making 4 sigma bonds. Or can I say it is sp3 hybridized and tetrahedral? Yes, as opposed to all the other carbons in the benzene ring, which are sp2 hybridized. So this becomes sp3 hybridized, and therefore we call this 4-valent because you see the valency on this is 4, you have 4 bonds attached to it. So this right here is a 4-valent carbocation intermediate that we have made. Now, why do we call this the intermediate and why is this not the product? Because benzene loves this pi ring because this is what gives it stability. So the stability of benzene depends on this pi ring. So we need to reform this pi ring. You can't stop the reaction here because right now this is unstable because the pi ring is broken. So you need to regenerate or reform this pi ring. So let's see the second step. What happens in the second step? The H is expelled. This H is expelled as H plus, and the reformation of pyrene occurs. So let's see that. So you have your 4-valent carbocation intermediate. So let's see, you have your 4-valent carbocation intermediate. Yes. And now this H plus this H is expelled as H plus. So what it will do is it will break this bond and both the electrons will go back in the ring. One electron goes in the ring and it reforms the pi ring, and the other one stabilizes the positive charge. So both the electrons from this bond, they will go back in the ring, they will stabilize the pi ring. So you will show it like this. It will be an arrow from the bond into the ring like this. And this H will be expelled as what? This will be a fast reaction, and H will be expelled as H plus, and your pi ring reforms, right? And the H is expelled as H plus. Let me repeat. In the first step of electrophilic substitution, you will have the benzene ring with the electrophile. The site of the electrophilic attack is the pi ring, and the electrons are in the pi ring. That's why you will show the arrow from the ring to the electrophile. And that will break this pi ring, and it will make a positive ion right here with 4 bonds, right? Therefore, we call it a 4-valent carbocation intermediate. Now, this H that we have attached to the carbon with the electrophile, this H will be expelled as H plus. So what happens is you will show an arrow in the second step from the bond to the pi ring. You will show the arrow going within the ring. This will be a fast step, and this pi ring reappears and reforms, and the H is expelled as H plus. Clear? Now, you see that electrophilic substitution is occurring in 2 steps. So if I make an energy profile diagram for this, it will be in 2 steps. So let's see how that would look like. So this is what it would look like. You will have this right here, the first step. Then you will have the second step. And this right here would be your final product, right? So we can call this step number 1, step number 2. If I ask you where will be our 4-valent carbocation, it will be right here, because this is where we have our products for the first step. So right here you will have your 4-valent carbocation intermediate. So this intermediate is right here. Clear? So this occurs in 2 steps, and they have been shown right here on the energy profile diagram. Now let's see. Before we see an example of electrophilic substitution, let's first see some points that need to be taken into account before you do the reaction. Now, the first thing is that prior to electrophilic substitution, before you start with electrophilic substitution, you need to make the electrophile. So we need to make the electrophile, and this electrophile is made in the presence of a catalyst. So this is made or produced, make the electrophile which is produced in the presence of a catalyst. And I will just show you when we see an example how we make the electrophile. So this is in the presence of a catalyst. Then you have, once the electrophile is formed, the electrophile attacks the pi ring. So this attacks the pi ring in the benzene and forms a 4-valent carbocation intermediate. Yes. Once you have this 4-valent carbocation intermediate, this is followed by expulsion of H as H plus. So there will be expulsion of H as H plus, and you will get your product. Now, if you look at the substitution reaction and you compare it to addition reaction, substitution reactions are favored more as opposed to addition reactions. Let's see why. If you see in addition reactions, the product does not have a pi ring. Do you see that? And I told you that the stability of benzene depends on the pi ring. So since the products in addition do not have the pi ring, therefore they are not as stable as opposed to these reactions. Substitution reactions reform the pi ring. Do you see that? So substitution is favored more as opposed to addition. So substitution reactions are favored over addition reactions in benzene due to the pi ring being reformed in substitution reactions. And we know that the pi ring confers to the stability of benzene. So the structure of benzene, or the presence of the structure of benzene, is stabilized due to the presence of pi ring. Clear? Now we have halogenation. Let's see an example of this reaction, electrophilic substitution. I've shown you the mechanism somewhat. Now let's see that using an example of halogenation. The first one, I am using chlorination as an example. Now for chlorination, the first thing you got to do is make the electrophile. How will we make the electrophile? In the presence of a catalyst. So you will take chlorine in the presence of anhydrous AlCl3, which is the catalyst. Now, why do we use anhydrous? What do you mean by anhydrous? That means it does not have water. Now, why do we use anhydrous? So anhydrous AlCl3 is used as a catalyst without water, because with water, AlCl3 will hydrolyze. Yeah, so AlCl3 hydrolyzes in water. So you use anhydrous AlCl3. This is your catalyst. Now, before I show you how the electrophile is made, let's just first see the overall reaction. This is the overall reaction. You have a benzene ring with chlorine in the presence of AlCl3 catalyst. And what will we make? We will replace one hydrogen with a Cl. That one hydrogen with the other Cl here will make HCl. So this is our overall reaction. Now we will see how these things are made step by step. So let's see the question. Briefly describe the mechanism of electrophilic substitution in benzene. So we're doing chlorination. The first thing that we got to do is produce the electrophile in the form of E plus or Cl plus. Yeah. So you take chlorine in the presence of AlCl3 to make AlCl4 minus plus Cl plus. Let's see how we made this. So you have chlorine, which is Cl2. You have Al, Cl, Cl, Cl. So this is what you have. Yeah. Now, if you see here, aluminum has a vacant orbital. Yeah, do you remember dative bonding from AS? Aluminum has a vacant orbital because it has 6 electrons around it. Now in chlorine right here, chlorine can make only one bond. Yes. So what will happen that this bond will break. Both the electrons will go to this Cl, making it negative. Yes, and I'm putting the lone pair right here. Or I can show it like this actually. So this has a lone pair and this gets a negative charge because it gains both the electrons. Yes, gains both the electrons and becomes negative. So this one will become positive because it has lost its electrons. Now you have a lone pair here. This will make a dative bond with the Al because Al is has a vacant orbital. So Al has a vacant orbital and Cl has a lone pair. Yeah, so they will undergo dative bonding. And what will we make? AlCl3 with a Cl minus will make AlCl4 minus. Do you remember? H2O with H plus used to give H3O plus. Likewise, AlCl3 with Cl minus will give AlCl4 minus. And this will be released as Cl plus. Do you see you have formed your electrophile? How? Let's see it again. You have Cl2, AlCl3. This bond breaks non-homolytically, like heterolytically, right? And both the electrons go to this Cl, right? This Cl has gained one electron of this one, and this one has lost its electron. So this has a positive charge, this has a negative charge. This one has a lone pair, this Al has a vacant orbital, so there will be dative bonding between them. And this will give you AlCl4 minus, and this will be released as Cl plus. Clear? You have made the electrophile. Now, I told you production of electrophile is not part of electrophilic substitution. Substitution just has these two parts. You need to make the electrophile before substitution. All right. So this right here is not electrophilic substitution. This is production of electrophile prior to substitution. Now, let's see electrophilic substitution. There are two steps. I told you in the first step what will happen. We will have our benzene ring, this with a electrophile, and there will be an arrow from the ring to the electrophile. And what will we make? We will make a 4-valent carbocation intermediate. So this right here is what you make. A 4-valent carbocation intermediate with a Cl here and an H here. Yes? Now you will take this 4-valent carbocation intermediate, and in step number 2, we will expel the H as H plus. So you expel this as H plus. Now let's see the products that we had formed here. We had formed Cl plus, which was our electrophile, which we have used right here. And what was the other product? AlCl4 minus. So we will take that AlCl4 minus over here. Now what will happen? This H, you will show an arrow from the bond inside the ring to reform the pi ring and to expel the H as H plus. And what will happen when H is expelled as H plus? That H plus with the Cl minus will become what? HCl. It will become what? HCl. So you have the Cl here. The H will be expelled as H plus. With the Cl minus, it will become HCl. And this AlCl4 minus loses the Cl minus, so it will reform AlCl3. And that's important. Why? Because AlCl3 was the catalyst. It should remain unchanged. Do you see it is regenerated? Because catalyst should remain unchanged. And how did we make HCl? We made HCl from the H plus that was expelled along with the Cl minus. H plus Cl minus makes HCl, and AlCl4 minus becomes AlCl3. So this is our product. We have chlorobenzene as a product. We will have HCl. How? H plus. Where is the H plus coming from? This H. And Cl minus from AlCl4 minus. They make HCl. And the AlCl3 is the catalyst which is reformed. And that's what it should be. Catalyst should be regenerated. That's what you see. Now let's see one more thing here. If you look at AlCl3, can I say AlCl3 right here is accepting a pair of electrons or a lone pair of electrons? Yes. Can we say AlCl3 accepts a pair of electrons? Yes. And we did this in transition also. I told you anything which accepts a pair of electrons is called a Lewis acid. So this right here is a Lewis acid. An electron pair donor is called what? A Lewis base. So just know that AlCl3 acts as what? A Lewis acid, which is that it accepts a pair of electrons. Clear? Is this understood? I want you to try the mechanism of electrophilic substitution of benzene with bromine. It will be exactly the same as chlorination. All you got to do is replace the Cl with Br. That is it. Is this clear? Is this understood?